So in this video, we will deal with chapter 14 of the health physics book, that is about the non-ionizing radiation safety. So what exactly is non-ionizing radiation? Non-ionizing radiations are electromagnetic radiations whose quantum energy is less than 12 eV. So even though here we're defining them as non-ionizing radiation, which the name implies that they don't ionize or cause ionization, but they still can do that because there are some atoms or molecules that need energy as low as 3 eV to cause ionization. One example can be a sodium atom. So in a sodium atom, if you want to make an ion by removing an electron, the minimum amount of energy that you need is 2.3 eV. So you can also cause ionization with non-ionizing radiation, even though in very small amount. So through the passage of time, we have had a good deal of experience about the damage non-ionizing radiation can cause to us. Some examples of the damages are given here. For example, it can cause damage to our eyes from observing solar eclipses. Then there can be damage from exposure to UV light among welders, from exposure to infrared energy among glass blowers and steel workers. Then we can get skin damage to from infrared and UV radiation. But the main concern about non-ionizing radiation first began after the war, when there was a boom in electronics and communication industry, and when people started using lasers left and right. So there was a lot of use of non-ionizing radiation in mass proportion that caused people to pause and think, okay, do we need to monitor and regulate these type of radiation as well? So keeping these thoughts in mind, there was a focus on the possible public health aspects from NIR, that is non-ionizing radiation. And eventually the US started a Radiation Control for Health and Safety Act, and this act was passed in 1968. So the purpose or the aim of this act was regulating the hazards from consumer electronics products. And then in 1970, they passed another act called Occupational Safety and Health Act. So the purpose of this act was to protect workers from hazards including ionizing and non-ionizing radiation that came from their occupation. So the entity we know very well is ICRP, which is the International Commission on Radiological Protection. But ICRP is not responsible for non-ionizing radiation. It has its field limited to the interest of ionizing radiation. But there is also another entity that's called IRPA, which is the International Radiation Protection Association. So IRPA has actually revised its constitution in 1977 and has expanded its area to activities to include the non-ionizing radiation as well. So now we have basically three entities looking after non-ionizing radiation. So let's see the units that are used for non-ionizing radiation. So basically there are two units. One is the photometric system and the other one is the radiometric system. So what does the photometric system of units measure? They measure illumination. So photometric units relate to the response of human eye to light. So this is the work of the photometric system. And then we have radiometric system that basically measures, that has absolute physical units that define the entire EM spectrum. So photometric is just for the response of human eye to light, and radiometric is for the whole EM spectrum. And energy levels of non-ionizing radiation is usually expressed in terms of wavelength or frequency. Now let's see some of the non-ionizing radiations like UV, laser, infrared, etc. etc. So let's look into UV light. So how do we define UV light? So WHO has defined UV light as light with wavelengths between 100 nanometer and 400 nanometer. So it lies on a range from 100 nanometer to 400 nanometer. But then we also subdivide this range into different regions. So from 100 to 280 is one region, from 280 to 320 is one region, and 320 to 400 nanometer is another region. So 320 to 400 is the UVA region, and then from 280 to 320 nanometer we have UVB, and from 100 to 280 we have UVC. So these are the subsections for UV radiation. And then here are some sources mentioned for UV radiation. If you can look into that if you're interested. So there are a lot of places we get UV radiation from, for example, hydrogen lamps, mercury lamps, plasma torches, printing ink polymerization, welding arcs, black light lamps. So a lot of lamps, right? So yeah, these are a lot of sources for UV radiation. Then let's come to laser. So I think we have studied this before in our high school as well. What exactly is laser? It's an acronym that stands for light amplification by stimulated emission of radiation. So there you go, that's your laser. So it's a device that is used to produce monochromatic light. So monochromatic light in the EM spectrum with visible UV and infrared regions. So this is a monochromatic light in the UV, visible and infrared region of the EM spectrum, in which all the waves are in phase. So the waves have to be in phase as well. So the beam is coherent both in space and in time. Now, we are not going to go through a lot of details in this chapter. We just need to know a bit of summary about how radiation, non-ionizing radiation can affect us and how we can protect ourselves from these. So that's basically everything written in the summary. So let's go through that. So what it first describes is what the UV region is. So UV light, as we have already said, is wavelengths, EM spectrum wavelengths from 100 nanometer to 400 nanometer. Achha. The biological hazard from UV light is basically to the eye and to the skin. So what is the hazard to the eye? It can cause cataracts in the eye. And what is the hazard in the skin? It can produce erythema and skin cancer. So these are basically the three hazards from UV lights. And then comes how we can protect ourselves from UV rays, right? We can use protective clothing, we can use sunblocks, and we can use sunglasses. So these are the main three effective things we can use against UV rays. Then we have laser. So again, firstly, it defines what laser is. It is the radiation in UV, visible and infrared portion of the EM spectrum, and have all of these in phase. And then its wavelength ranges from 100 nanometer to 1 millimeter. So that's the range of laser. And then we have microwaves, whose wavelength range from 1 millimeter to orders of meter. So as we're going to this direction, the wavelength is increasing. Then we have radio frequency wavelength, which range from meters to kilometers. So this is high school physics. You should already know this. So what's the hazard or biological hazard from lasers? So it's basically the same as UV rays. The main biological hazard is to the eyes and to the skin. And the maximum exposure level from the laser source depends on some factors, mainly the characteristics of the source and the exposure time. So how much you're getting exposed depends on characteristics and the time. So what falls under the characteristics category? So wavelength, whether the laser is pulsed or continuous wave, and also the duty cycle of the laser. So these things fall under the characteristics of the laser, and then we have exposure time as well. So how do we limit exposure from non-ionizing radiation? So we use certain units such as radiant exposure, that is in joule per centimeter square. So we can either use radiant exposure, or we can use irradiance, that is in watt per centimeter square. So we can use either of these two units. Then we have radio frequency and microwave radiation. So what kind of effects do these things have? So they basically have thermal effects. So they can have either thermal effects, and the other effect they can have is due to the realignment of molecules and electric fields within the body. So it can cause realignment of molecules and electric fields within the body, which is something we don't desire. And then the quantity of the dose from radio frequency and microwave is and specified with specific absorption rate, that is acronymed with SAR. So we can quantify it with specific absorption rate, and is measured in units of watts per kilogram. So it's written here, specific absorption rate is measured in watts per kilogram. And then overall, the radiation safety measures we take from these sorts of radiation is minimizing our exposure time. So minimize time, maximizing the exposure distance from the source, and also interposing shielding. So this is something you will see in ionizing radiation as well. How we can minimize radiation to our body is by minimizing exposure time, maximizing distance from the source, and also using shielding in between us and the radiation source. So that's basically it from non-ionizing radiation.